Assalamu alaikum wa rahmatullah. This is Shady Elkassas, Sharjah American International School, and today we're going to discuss some ideas related to the entrance exams that you're going to have for some universities. The entrance exam in physics is one of the requirements for some universities in order to apply in engineering or medicine. So it is very important to be able to be aware of the basic concepts in such exam. The points that we're going to cover today are 4 basic points. This is part 1 of our revision, and we are going to cover the following points. First of all, we are going to cover the SI units. Then some ideas related to convergence. Then we are going to cover the dimensional analysis. And then we are going to cover the significant figures. So let's begin with the SI units. The SI units basically are the international system of units, and this international system of units is a common system that scientists are using in order to interpret their data. So SI units stands for the international system of units, and it is classified into 2 main parts. The first part is called base units. The other one is a derived unit. The base units describe one single dimension, and I mean by one single dimension, one physical quantity at a time. So, for example, if we said that you need to measure the mass, so we use kilograms for the mass. For time, so this is for mass. For time, we use seconds. This is for time. For length, width, height, distance, displacement, we use meters. Length, width, height, and so on. We use Kelvin for temperature. We use liters for the fluids volume. And I mean by fluids, I mean gases and liquids. And we use mole for the amount of substance, joules for energy. Sometimes they mention candela for the illuminance intensity, so let's add it. It's for the illuminance intensity. This is related to light. So we have 7, if you added candela, it would be 8. So 1, 2, 3, 4, 5, 6, 7, and 8 base units. The combination of 2 or more base units will give you derived units. So it describes more than one dimension. Let's say that we need to measure the area, so you use meters square, which is for the area. So it is meters times meters, which means it's a derived unit. It has more than one dimension at a time. It has 2 lengths dimensions. So here we have added a length and a length, we multiply 2 length dimensions, and you found the area. Then let's say we need to measure the volume for solids. You will use meters, cubic meters, or meters cube. For velocity, for example, you use meters per second. This is for velocity. And it has 2 dimensions, meters and seconds, which means length and time. Acceleration, meters per second square. This is for acceleration. If we combined mass and acceleration, so kilograms dot meters per second square, you will find force. and this is equivalent to newtons. This is the same as newtons. If you combined the velocity and the mass, kilograms for mass and meters per second for velocity, you'll find the unit for momentum, which is P is equal to m times v. And as you can see, you have many units in here. And these units could be the same, like meters squared and cubic meters, or you may have different units, which just like the meters per second and meters per second squared and so on. So these are the SI units, base and derived. Let's move on and let's discuss the convergence. Before we discuss the convergence, you need to know that in convergence you have two types of prefixes, and those prefixes prefixes, and those prefixes are summarizing the very big and very small values as powers of 10. So you have positive powers of 10 like kilo, mega, giga, tera, and peta, and you have very small powers of 10 like centi. Let's start with deci. Deci, centi, milli, micro, nano, pico, and femto. And as you can see, all of them are small letters. Kilo, mega, giga, tera, and peta are big powers of 10s, like 10 to the power of 3, and then 10 to the power of 6, 10 to the power of 9, 10 to the power of 12, and 10 to the power of 15. While here, this is centi, milli, micro, nano, pico, and femto, 10 to the power of negative 1, 10 to the power of negative 2, 10 to the power of negative 3, 10 to the power of negative 6, negative 9, negative 12, and negative 15. If you wanted to memorize those, so you can just say, Dad called me micro, not pretty funny. Dad called me micro, not pretty funny. And this one, you can remind yourself of the computer's storages, like kilobyte, megabyte, gigabyte, terabyte, and petabyte. This would be in the future. The question now is, how can I convert from one unit to another, from one prefix to another? This is now the question related to conversion. In order to convert, let's have examples of questions related to conversions. Let's say that someone needs to convert 3 kilograms to, let's say, milligrams, 5 nanometers to micrometers, 3 centimeter square to millimeter square, and finally, let's say 2 times 10 to the power of negative 2 millimeter square to centimeters cube. Let's use the cube here. Cubic millimeter and cubic centimeter. So you have many ways to convert from one prefix to another. You have the stairs method, which is mentioned in the books and references, but I have one easy step or one easy method that you can use, and we call it translate and flip. Translate and flip. Translate the left side and flip the right side. And I mean by translate, I mean to put the meaning of the prefix. If it's 10 to the power of 3, put it 10 to the power of 3. If it's 10 to the power of negative 1, put it as it is. So you're just putting the meaning of the prefix. For flipping the prefix, I mean you need to convert or to flip the sign. If it's positive, make it a negative, and vice versa. So let's apply the translate and flip method. So in here we're going to translate, and in here we're going to flip. Let's do it. So this means that 3 times kilo is 10 to the power of 3. I'm going to translate it. Times milli. This is a milligram, and the milli is 10 to the power of negative 3. So I'm going to flip it to 10 to the power of 3. I'm flipping everything in the right side. And then continue your multiplication. 3 times 10 to the power of 3 times 10 to the power of 3 is 10 to the power of 6. We are adding the powers. And then don't forget to put the final unit, which is milligrams. So this is your final unit. It's a matter of seconds, and you will be solving the problem of converging. And I know that this causes a headache for some of our students, so from now on it's not going to be a headache by any means, because you're just translating and flipping. Here 5 nanometer and 2 micrometers. So let's say that 5 times, what do you think? Nano is 10 to the power of, exactly 10 to the power of negative 9, times micro is 10 to the power of negative 6. So I'm going to, wonderful, I'm going to flip it. So it would be 10 to the power of 6, which is the flipped value. And then it would be 5 times 10 to the power of negative 9, and 6 would be negative 3. Don't forget to put the final unit, which is micrometers. 3 centimeters square, 2 millimeters square. And here you can discover the value of this method, because it is working even with the squares value and the cubic value here. 3 translate 10 to the power of negative 2, but you need to respect the square, so square. So I'm just translating the centi as we have made here in the other problems, but we need to put the square because it is mentioned in the problem. Multiplied by milli. Usually we flip this, so yes, I'm going to flip it. Milli means 10 to the power of negative 3, so it will be 3, but we need to respect the power, so put the power. And then you can continue your problem by making your processes as usual. So in here you're going to multiply the powers. 2 times 2 is 2 times 10 negative 2, it will be 3 times 10 to the power of negative 4 multiplied by 10 to the power of 2 times 3 is 6, and then you finish your problem. 3 times 10 to the power of negative 4 and 6 is 2, and put the final unit millimeter square. You are done. Here also in the conversion for the cubic centimeter and cubic millimeter, you're using translate and flip. So 2 times 10 to the power of negative 2, this is the number given in the problem, so you need to put it as it is, multiplied by, you need to translate the milli, which is 10 to the power of negative 3, but we need also to respect the power, multiplied by centi is 10 to the power of negative 2, and we usually flip this side, which is 10 to the power of 2, but we need to respect the power, and then you finish your problem. So it would be 2 multiplied by 3 times 3 is 9, 2 times 3 is 6, which would be negative 3. The total would be negative 3. Negative 3 and negative 2 would be negative 5, so negative 5 centimeter cube. Let's check the calculations one more time. 2 times is 6, negative 3 and negative 3 and negative 9, so negative 3 and negative 2, yeah, negative 5 centimeter cube. So this is the way of solving the prefixes. Then let's go to the dimensional analysis. And in the dimensional analysis, it means that you need to put your values in terms of mass. So the dimensional analysis, it means that to put your values in terms of mass, length, and time. This is a very easy task, but the secret of this problem is to get the unit of the value that you have. Let's say that I have given you this problem, which is saying that consider that area is equal to length times width. Find the dimensional analysis of area. So first of all, I need to find the unit. The unit of area, length times width, is meters times meters, which is meters square. And meter square is, do you think it's a mass, length, or time? So exactly, it is length value but square. So this is the dimensional analysis of area. Let's have another problem. Let's say that we have velocity. Velocity, for example, is equal to displacement over time. Find the unit, which is meters per second. Make it division seconds, because this way you're going to ease the problem for yourself. Meters per second, which is a division problem. Meters per second. So what do you think the dimension of meters? Is it mass? Is it length? Is it time? Exactly, it's a length divided by seconds, which is exactly time. So it is length over time, and this is the dimension analysis of velocity. Let's go further for the acceleration. Acceleration is delta v over delta t, which is equal to delta v, which is velocity, or the change in velocity, and it has the unit meters per second square, multiplied by 1 over delta t. Delta t is seconds. And as I told you earlier, you need to use the division. It is easier for you in order not to be confused in the denominators and numerators. So meters per second square, sorry, here we are mistaken. It is meters per second is the velocity, and 1 over second, it is the time. So it is meters over second, which is velocity, 1 over second, which is the time. The time here is down, so it is 1 over second. And then combine both, you will find it is meters per second square. So let's get the dimensions. It would be L over T square. And this is the dimension analysis of the acceleration. Let's go further and let's discuss something like momentum is equal to mass times v, velocity. Put the units, kilograms dot meters over second, meters per second. And because it is a multiplication process, so the S can be for both the kilograms and the meters. So let's translate it into dimensions. You cannot simplify this more than that. So kg is a mass, m is a length, s is time, so ml over t is the dimension analysis for the momentum. Force, for example, is equal to mass times acceleration, so it is m times a, which is a kg multiplied by the unit of acceleration, if you do remember, wonderful, meters per second square. So it is equal to m L over T square. Let's have more examples. For example, let's say that I need the unit of, or dimensional analysis of the work. Work, for example, is equal to F times D. So it is Newton dot meters. But again, I need to get the newtons in more detailed units. So the Newton is a kgs, kilograms, meters per second square, because it's a force. And meters is a meters, keep it like that. So kg meter per second square is the newtons, and the meters is a meter here. Make it more simple, it would be kgs meter square per second square, which is equal to mass L square over time square. So this is the dimension analysis of work. Let's have another example. potential, let's say the kinetic energy, for example. Kinetic energy is equal to half mv squared, the mass and velocity squared. Let's get the unit. Half basically has no unit because it's a constant, it's a numerical constant, but the mass has a kgs, and the velocity is meters per second, but it is a squared value, so meter squared and second squared, because there is a square on the velocity. You cannot simplify it more than that, so kg is m, a meter square is L square over T square. Can't you notice something here, which is that the work dimension analysis has the same dimensions of kinetic energy? Isn't it weird? Well, it is not weird if we knew the definitions of work and energy in general, because the work, the energy is the ability to do work, so basically they are related. If you do remember the kinetic energy relationship with work, that work is equal to delta Ke, which is Ke final minus Ke initial. So the change of work, the change in energy gives you work. So they would be having the same dimensions. Let's prove this further by getting the dimension analysis of the potential and gravitational potential energy, GPE, which is equal to mgh. M is a mass, g is an acceleration, this is the gravitational acceleration, 9.8 meters per second squared, and this is the height, which is a value also. So let's get the dimensions of the three values here. Mass is a kgs, g is an acceleration, so it is meters per second squared, and the height is a meters. Simplify it, so it would be kgs meter square over second square, and you will find that kg is an m square is L square, and S square is time square. And we have proven that both or the three values, the work, kinetic energy, potential energy, they have the same dimensions, which means that we are correct. So enough now for the dimension analysis. Let's move to the significant figures. So before going into the significant figures, you need to know how many significant figures in a specific number. So let's say that we have 1000, let's say we have 0.0002, let's say that we have 0.00 here, 102, let's say we have 20, 10002. So how many significant figures in here? How many significant figures here, here, and here? So the rule is, if you have zeros to the right side of the number without decimal point, so those are not significant. So you only have one significant figure here. Here, those zeros are to the right of the number and they are not between non-zeros. So 0.000, this is not, these are not significant by any means, but the 2 is significant, so this is one significant figure only. And this is an important rule in the significant figures. If you have zeros to the right of the number, only zeros, and there is no decimal point, they are not significant. If you have zeros on the left side of the number, only zeros, there is no non-zero digit, so this is also a non-significant. If you have many zeros between non-zero digits, here this is a non-zero, here this is a non-zero, so they are significant. So all of them, all of these numbers are significant. So 1, 2, 3, 4, 5. 5 significant figures. What about here? Well, don't jump into the conclusion that 0 is to the right of the number, so it's not significant. I said here, zeros to the right of the number, and there is no decimal point. But here, there is a decimal point. So the decimal point gives the 0 on the right side a VIP card. So it is significant here. So we have 1, 2, and 3 significant figures. What about this? This is easy because the zeros are between 2 non-zero digits. So all of them are significant. 1, 2, 3, 4, 5, 6. So 6 significant figures. Okay, let's have an exercise for you. If I said that 2.0000, what do you think? Exactly. They are to the left, but there is a decimal point. All of them are significant. 1, 2, 3, 4, 5. 5 significant figures. What about this? Exactly, 1 significant figure. What if I did that? 0, 0, 0. Exactly, the 1, 2, 3, 4 of them are significant because those are on the right side of the number, but there is a decimal point, so it gives it a VIP card, which means it's going to be significant. So those are the significant figures, and this is the rule of the significant figure. Now let's have some ideas about how to add and multiply, divide and subtract significant figures, and let's follow the rules of the significant figures. So simply following the rules of the significant figures is easy because multiplications and divisions problems are having the same rule, while addition and subtraction are having the same rule. Multiplication and division, they have a very simple rule, which is the least number. Here, the least after the decimal point. I will explain what do I mean by these two secrets. So let's say that we have two numbers multiplied by each other. So 2.2 multiplied by 1.012. Let's say that we have 2.2 plus 1.012. How can I apply significant figures in those two problems? So in order to do that, we need the calculator. So let's solve this problem. First, 2.2 multiplied by 1.012. So it gives you this number, which is 2.2264. Let's also perform the addition. 2.2 plus 1.012. So it would be 3.212. Okay, so what is the rule of the significant figures in both problems? The rule is, here I told you follow the least number. Let's add the word follow. Follow the least number. Here follow the least number after decimal point. The meaning of this rule is follow the least number. You need to have a result, which is this one, that looks like the least significant figures here in the problem. So let's count the significant figures in the problem. 1, 2, here 1, 2, 3, 4. So what is the least significant figures here? This is the one, which is 2 significant figures only. This means that according to my rule in the multiplication division, we need to have the resulting number to look like the least number here. So this number should be 2 significant figures only. So make a box like that around the 2 significant figures here and look outside the box. This is a 2, so it's a rounding down number, it's not a rounding up, which means that the 2 will remain 2.2, and this is your result. And look at that, your result has the same amount of numbers of significant figures. This is 2 significant figures, this is 2 significant figures. Let's have another problem in order to make it clear, because this is multiplied by 1, so it looks like the same number, but you know, we need to choose some bigger numbers in order to clarify the idea. So let's have another example on the significant figures. So let's say that we have something like 6.36 multiplied by 3.258. So the result would be 338.72088. So following the rule of the significant figures in multiplication, you need to count the whole number. So 1, 2, and 3 significant figures, while here 1, 2, 3, 4, 5. So your number should be 3 significant figures because this is the least. So your number, make a box around the first 3, 1, 2, 3. Look at outside the box. 7 is a rounding up number, so it would be 3, 3, 9. So these are your 3 significant figures, which looks like the least here. In the addition, let's add the same numbers. 6.36 plus 3.258. In addition, as we said, you need to follow the least after the decimal point. So I'm not going to look at the whole number. I'm going to look at the least after the significant figures. So after the decimal point, I'm not going to count the whole number. So I'm going to count those. After the decimal point, I have 1, 2 significant figures, while here I have 1, 2, 3. So your result should be 6.36 plus 3.258. Your result from the calculator is 59.618. Look at the after decimal point. I have to have 2 numbers after decimal point because this is the least after decimal point. So 1, 2. So make square here. Your number should be 59.6. Before writing the 1, look outside the box. What is the number outside here? Is 8. Is it a rounding up or rounding down? Exactly, it's a rounding up, so this one should be 2. So this number has the same amount of significant figures after decimal point like the least one in here. Let's have another example or the addition. Let's say 6.2235 6.2235 plus 11 plus 11.2. So your result should be 17.4235. So it's an addition problem. I'm not going to look at the whole number. I'm going to look at the number after decimal point. So after decimal point count 1, 2, 3, 4. After decimal point it's only 1. So this is your number. So I'm going to have 1 number after decimal point only. Make a square. It's 17 point. Before writing the 4, look outside the box. Is it a rounding up? No, it's a rounding down. So it will remain 4. So this is the addition. So these are the two rules of the significant figures. If you have multiplication division, you need to follow the least number, the whole number. You are counting the least, and your result should be having the same significant figures like the least number. While in the multiplication and the addition and subtraction, you need to have the least numbers after the decimal point. So you are looking after the decimal point. So now we covered the four problems or the four objectives that we planned here. So we covered the SI units, the convergence, dimensional analysis, and significant figures. I hope that this session was beneficial for you. If you have any questions or comments, please just post them as a comment to this video. This was Shady Elkassas, the Head of Science Department, Sharjah American International School. Have a good day. Bye-bye.